All right, everyone. I am here with Julie Shah. Julie is a professor at MIT. Julie, welcome to the TWiML AI podcast.
Thank you so much for having me.
So you are a professor of robotics in particular, and we're going to dig into your work in that field. But to get us started, I'd love to have you share a little bit about your background and how you came to work in the field.
Wonderful, yeah. So I'm a professor of aeronautics and astronautics at MIT, and I also lead a robotics lab at MIT as a part of the Computer Science and Artificial Intelligence Laboratory. And I have a special love of like time critical, safety critical applications, which is why I'm in aerospace. And so my story of how I ended up in robotics has to start with how I ended up in aerospace. And I was just like born loving airplanes and rocket
Uh-huh.
ships. I always wanted to be an astronaut. And I looked at, there was like I went to space camp. I was a super nerd.
Oh,
Um,
nice.
which I'm very proud of. And at space camp, they give you a book of all the astronauts and where they all went to school. And they always stress you need to be really good at math and science. And I was like, check, I can be good at math and science. And
Yeah.
a very large number of them either went to the military academies or MIT. And I
Uh-huh.
was like, MIT sounds like a good place. And so whenever anybody would ask what I wanted to do, I would say, I want to go to MIT and study aerospace engineering. And everybody would say, oh, that's so specific. What's so specific? And I'd say, okay. And then I came to MIT and I in the Aero Astro department. And then, pretty soon after in the department, I'd be asked, okay, so you're Aero Astro, but what are you going to specialize in? And I was like, oh
Uh-huh.
no, I have to specialize further. As it turns out that, aerospace, much like robotics, it's a systems discipline.
Yeah.
And I really loved control theory and control systems, and really loved learning about aircraft autopilots, and how those really had to be designed to the capabilities of pilots, of humans, and how they could affect control over a system. Having to design for the human machine system was
Mhm.
really exciting to me, and needing to understand both sides of that equation. Um, so I actually did my master's degree in human factors engineering, to kind of go deep on the human side. And it wasn't until my PhD I switched gears, and joined the Computer Science and Artificial Intelligence Laboratory and did my PhD in automated planning and scheduling. And so, this was 2010. I finished up my PhD, so before the big, the big era change to machine learning, and throughout have just been really, really interested in how you design automation and technologies, and AI and machine learning to like fit like a puzzle piece against human capability, so that you can sort of achieve some end objective. And that's why I started a robotics lab, the Interactive Robotics Group, and my lab includes human factors engineers, and includes aerospace engineers and computer scientists, and others as well. So we bring kind of a cross-disciplinary perspective to developing the technology and showing its benefit.
Nice, nice. In your lab, do you still have that leaning towards flying robots as opposed to arms or walking robots or humanoids or other types of form factors?
Yeah, it's interesting. It's interesting you ask that, because when I applied for faculty positions, it was straight out of PhD, and I got the offer from MIT from my home department. I did all my degrees at MIT, and then I had this amazing offer from MIT from my home department. But they strongly recommended slash required that I go away for a year before starting on the faculty. And my PhD was funded under an NSF fellowship, so it was
Uh-huh.
maybe not super closely tied to real applications of real systems. And the department head at the time suggested that I go out to Boeing, and he said, they have interesting applications in robotics for manufacturing. I said, oh, that sounds great. Sounds like a great way to spend a year out in Seattle. So,
Yeah.
um, and I just caught the bug of manufacturing. I just loved watching a 737 or a 777 being built in front of me, and then thinking about the challenges. Again, it's like an integration challenge. Like robots can do pieces of that work, but actually the vast majority of building a large commercial airplane is still done manually, like a beehive of manual work. And so there are challenges in how you design the technology, the robotics, the intelligent robot to integrate into manual workflow. Um, And so when I came back, I had I wanted to keep doing that. I kind of wanted to keep working in robotics for manufacturing and collaborative robots. And I asked a different department head, the one that hired me at the time, said, "Is it going to be okay if if I work in manufacturing in Aerostro, or do I need to be flying things?" And he said, pursue the problems that you think are important." And I really appreciated that. I work on aerospace and applications, but I also work in automotive. I work in decision support for fighter pilots, but also like nurses and doctors. But the key thread is I think it's really exciting to develop technology that really has to be flawless to add value and has to fit with the human in a way that doesn't add friction, but really eases a very challenging job of a domain expert. And
So you
so,
can kind of envision that as a Venn diagram of, mission critical in one circle and requires human interaction in the other, and your sweet spot is in the middle.
yeah, yeah, that's a good visualization of of whether or
Nice.
not I take on a project. Yes.
Okay. And so let's dig a little bit deeper into that. What are some of the types of projects that you work on, or maybe even more broadly, how do you craft a research agenda in that intersection?
So I started on the faculty at MIT just a little over 10 years ago, or maybe 11 years ago now. And from the sort of like the vision behind our work then and still now is to be intentional about developing intelligent machines or intelligent robots, or even kind of computing more broadly, that enhances human capability and well-being. And um, and there are many ways to do that, but starting out in the lab and going back to my PhD, I was interested in how far can you get in developing a robot that can emulate the capabilities of an effective human team member. Um, and that's not the only model of collaboration or teamwork, for sure. And it's not even, it was always a hypothesis. It's not even a given that if you develop a system with some of the capabilities or features of an effective human team member, that'll even be useful. So we've always conducted experiments to try to determine whether or not that's useful. But my lab focuses on developing novel AI models and algorithms where the AI is modeling people. And so there are decades of studies in what makes for effective human teamwork, in sports psychology and studying pilots in the cockpit, or doctors and nurses in the operating room. And it's a very practical field of study, because you want to be able to train up new people to come into this profession and work effectively in a team. Um, and But I'll just brush that all aside and summarize many decades of very rigorous study in human teamwork and human team coordination. In terms of like there's three capabilities that we as humans bring to teams that make us really make some of us exceptional team members. And that's the ability to know what your partner is thinking, to be able to anticipate what they'll do next, and then be able to use that information online as circumstances unfold to sort of change your plan. And so my lab has focused on doing those three things: developing models that can infer human cognitive state, predictive models of human behavior and workflow, and then also a set of techniques around dynamic plan execution, to be able to take those predictions and use them online, to have a robot kind of play the game with you. It's primarily in development of novel AI models and methods, but everything we do needs to be tested and evaluated with a system actually working with a person, to know whether emulating these capabilities is even of value.
Well, one of the things that you said in there that I don't want to be as hyperbolic as blows my mind, but it is the idea of the robots or the AI kind of predicting what's going on in their human collaborators' heads. That's hard enough for a human. What does that even mean for a robot or an AI?
Yeah, that's a great question. So, and you have to pursue that in an academic fashion. It needs to be a well-defined problem, and the human cognitive state that matters in a particular setting, and particular setting A is very different than the state that matters in a different setting. sometimes when I give talks, like sometimes the question afterwards is there a unifying, model or approach to being able to infer human cognitive state? And I've always just been like, I don't think so, but we'd have to maybe ask the cognitive scientists and neuroscientists.
Yeah.
But I think that's a really, like, for me, that the fact that there isn't, one well-defined set of states that you're really after, that you're aiming to infer, is actually one of, like, the key research questions, and I think it is one of the key research challenges, which is like, we as humans, we want to be able to shape the machine learning model or the AI's model of our world or of us, much like a human brings, like, different considerations or a different mental model of interacting with another human or doing one task versus another task. Um, like, a key sort of direction of our research is first of all, recognizing that you will never succeed at that with an unsupervised learning approach. You might get super, super lucky, and the latent states you infer happen to correspond to the human's mental model of, what's particularly important in that particular context. But practically, that's not going to happen. And you know, um, theoretically, it's a challenge. So the question is, what inputs can you elicit from a person that's easy for a person to provide, that can help lock in or sort of shape the latent space or improve the efficiency of inference for the system to learn those, the latent states or their dynamics of the human that's interacting with it, and, like, providing labels, like a supervised approach will work, but then where do those labels come from, and how practical is it in every setting to be able to provide labels of relevant human cognitive state? I mean, it's just like an unreasonable request. um, so yeah. On the other hand, there are inputs that are easy for people to provide, like, I can maybe it's helpful to ground it in a concrete example. So, say I have the most simple system I'm trying to, develop my own mental model of, and it's just a subway. So it just goes to the end of the line, it turns around, and it comes back. I'm originally from New Jersey, so in New York, the subway goes uptown and downtown, and that's the mental model I hold as someone from New Jersey. But in Boston, the subway behaves exactly the same way. It goes to the end of the line, it turns around, and it comes back. But we say the subway goes inbound and outbound, and the switching point is some arbitrary, like, stop in the center, which is weird. So, like, you're going inbound as long as you're going to Park Street, and as soon as you pass through Park Street, you're going outbound. And then when it turns around and comes back, you're going inbound again until you pass through Park Street, and then you're going outbound. So it's like my mental model of the subway in New York and Boston. It's a two-state switching model, but my mental model is different depending on where I'm from. Um, and so, we employ, like, non-parametric Bayesian techniques to try to infer latent state, of, some black box system, say like a human. But what are the odds you're going to learn an inbound outbound switching model for Boston? It's like, you know but here's the thing, like, maybe I don't want to label for you inbound outbound, and then New York is uptown downtown. um, but if I can just tell you the change point, the switch point. So in New York, the switch point of my mental model at subway is that it switches at the end of the line, and in Boston it switches at Park Street. That's enough to sort of lock in. And now we're going to hold the same mental model of how to talk about the behavior of that subway. Looking for these ways in which it's very easy for a person to provide high level input into a machine learning model, and then enabling the machine learning model to use those inputs within its computational framework, um, is really, really exciting to me.
Are the inputs that you're talking about, and in particular in this case of the subway, is this an interaction time input, or is this a training input?
So the particular work that I'm talking about there, that's done at training time. So,
Okay.
the idea is, you have your time series data, but rather
Mhm.
than work with it in an unsupervised fashion, maybe you have some labels, but it's not fully labeled. And then you take this sort of high level input from the person in the form of partial policies or partial dynamics. And then what we do is we formulate those as constraints on a variational inference process. In that work, it's still done at training time. And I think your question is really exciting because, okay, so, or even you have a trained model and now you're taking your new task to do together, new environment, or how it is you, first of all, identify the differences between how you want the system to behave in the new environment or the model it holds and be able to adapt it is, online is, a really exciting research direction.
Yeah, I think where the question was coming from was in the context of training it, and me trying to construct what this trained model might look like. It almost sounded like a feature engineering task that a subject matter expert might apply, to map some raw data of whatever the data is we're looking at about these trains to their mental model of the world in order to get the model to kind of attach to that in the training process, to use loose terminology. You might, if you have your uh if you're kind of moving away from some center, you might, the your feature might be the distance from that center point or the distance from your endpoint or something like that. And I was trying to I was curious whether the way that you were building that knowledge into the system was similar to feature engineering, or was it a different process altogether?
That's interesting. So you're highlighting that, like, the person's role can be in identifying or synthesizing the features that are meaningful to their understanding of of the functioning of the system. There's definitely a role there, and also support. Obviously support there in enabling a person to uh, enabling the proper elicitation of those features. The particular work that I'm referring to, it's not in the feature engineering space. It's so we employ like a Bayesian graphical model, a factored model, with particular assumptions made on on the structure of the model to be able to support efficient inference. So you have a set of observable states about the world. Like, there's things I can see about the subway, right? I can see its movement. There's actions that are taken, that are observable, but then there's something in the latent space that clearly impacts the behavior, the observable behavior of the system, as I want to be able to predict it and describe it. And I think what's interesting is either of those two state switching models can be informative, right? Especially if you want to predict the behavior of the system. It's, you just kind of need a two state switching model, and you'll be able to predict the behavior of the system. But the 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 question of, like, which one of those, sometimes it can help in predictive power of your model, but it's critically important for being able to support a person in inspecting and understanding and doing their own projection of the behavior of this learned model in a different context. In the approach, it's really a flat. We assume a flat, discrete, latent state space. But the feature engineering question is equally important. I worked for a while on my pilot's license, which was really fun. And then I was a grad student and I ran out of money before I could solo, which was, I thought I had it all planned out, but you never fly for an hour. You always fly for an hour and 15 minutes, and it
Uh-huh.
didn't end up working out. And the irony is, now that I'm in the aero astro department, like, I think there's, like, actually a benefit, like a professional education benefit, where I could do flying lessons, and now I don't have time and I have young kids. So, but from my days of learning how to fly, like, it's just like much like a poor machine learning model. It's like a lot of input, and like there's spurious correlations. Like, you're like, oh, maybe I should do this when I see that over there, and it's like the role of the
Uh-huh.
instructor to be like, here's what you attend to. These three features mean this. Like, put your fingers up. Do you see the horizon above or before four fingers? Now you know if you're flying straight and level. And like that role of guiding the meaningful the meaningful use of the features that the system could attend to is enormously valuable. Without a causal model, it can be it can be challenging to ensure you're learning a model that'll produce the behavior that you hope it'll produce in a novel environment.
Hmm. Hmm. The is this subway example, is this a kind of a toy example for illustration, or was there an actual problem that you were solving, an actual data set, and what exactly is that problem?
Yeah. The subway example was the very most simple synthetic domain in the paper to like
Okay.
illustrate the idea of we applied it to be able to so in this larger goal of being able to observe a human and develop a predictive model of their behavior. Like a person holds certain priorities or preferences and how they want to do their work, and this is something like that is practically a challenge for us in deploying robots in industrial environments. So on an assembly line, someone might say, "Oh, there's standard work. There's like a standard way of building this car. Or there's a standard way of building this plane." And I believed that till I went in and watched how people build things. But there's actually like a whole lot of variation in how the plane is assembled or how the car is assembled. Um, and different people for different reasons, different biomechanical models will have different ways of performing the work. And in something like an automotive, an automotive factory, a collaborator once told me that like half a second of efficiency could like make or break the business case for introducing a new technology. So once you're looking at a robot to support a person and being like half a second faster, like small changes in the ordering of how they install, something on the dashboard of a car, or their motions, being able to predict where they'll be in a fine grained way for the robot to assist, that'll make or break the success of that system in doing that. So being able to quickly kind of lock in and model an individual person's priorities or preferences for performing a task improves the predictive power of that model. But the key is to be able to do it with relatively little data. So the concrete use case is a person does their assembly task in a factory, and you can collect data of how they do their work. And then you want to, when the robot comes in, you want to be able to model like their intent, like where they're going to reach next on the table, or where they're going to walk next in the cell environment. And different people have different, again, priorities and preferences. Workload or sort of fatigue level can impact your model of your predictions for the person. But rather than hand specifying a threshold based on some measures, it's better to be able to learn that and tune that threshold based on the value it gives you in order to predict where the person will be in space and time after some number of hours. So those are the sort of more concrete use cases of inferring these latent states and and especially their dynamics.
Got it. Got it. In the case of the shop floor and the preferences, kind of going back to that earlier question I asked about runtime versus training time. Training time, you've kind of built in the capability to identify this, but the identification is happening at runtime. Is that right?
Yeah. So, okay. So, this is this is this is fun. Okay, so like, what do you need for a robot to be able to collaborate with a person online? You need it to have a model of human behavior, which
Yep.
has, and it's maintaining a belief, right, over the person's latent states, and a belief over what they're going to do next. And then you need a task model, and maybe you're lucky enough to have a clearly specified task model. But even then, you have a partially observable model that the robot is reasoning about in order to be able to collaborate with the human partner. So that gives you is a POMDP, and then you want to be able to solve that POMDP online. And what does it mean to solve it online? It means to give the robot the ability to choose its actions, both its like physical actions or in some cases even communicative actions,
Mhm.
to be able to reason on the uncertainty of what the person will do, but also to be able to reduce uncertainty based on
And
its
just
own
to
actions.
quickly interject, POMDP is partially observable Markov decision process.
That's it. Yep. Yep.
And the it, going back to the beginning of your explanation, do you have one partially observable model, like you have this task model that is, um, in which there's some noise of what the human might how the human might perform that task, or do you have two distinct models, one about the human and well, it sounds like one is the human's cognitive state, which you're using to influence the task model.
Yes. Yeah. So the human's cognitive state is not directly observable. Therefore, the model of your human is partially observable. Like you can
Okay.
see physically what they're doing, but there's some elements about what they're doing that you can't directly observe. And because of that, the robot is aiming to reason about a part, about how it should behave or act, or what actions it should take, considering this partially observable model of human behavior. The task model, in some of our works, we assume it's fully known and fully observable. But just as it's really important to lower the barrier to quickly and easily learning a human model to work with a person, it's really important in many contexts to lower the barrier of enabling like a shop floor or a line worker or a domain expert to teach a robot a task without an applications engineer as the intermediary, or in our lab without your AI researcher as the intermediary. And when you aim to do that, you're no longer directly specifying the task, and it's often advantageous for the robot to maintain a belief over the true task specification as well. So it may not definitively know, the specification for how to perform the task, but to hedge against its uncertainty. Maybe in some particular context, it really needs to be very, very conservative. It's a safety critical context. In other contexts, it might have more flexibility without there being a major consequence. But that's another form of partial observability that would go into a POMDP model that includes both an agent model and a task model.
Yeah, I've come into contact with, well, not physically, but there are like these co-robots or cobots that are in use. I think there's a Baxter robot. Like there are models for humans interacting with robots, but I imagine they're fairly brittle when the human does something kind of outside of the script. Maybe the robot just waits for the human to get back in the right position or something like that to continue the script. And what I'm hearing is that this is a direction for building robots or robot AIs that can more gracefully interact with humans. Is that the big picture idea?
Yeah, that is the big picture idea. Like the big picture idea is to figure out how you can develop and field robots that don't require a human to be a robot to work with it. So, because that often doesn't work very well. But there are actually many of the applications out there today. I mean, humans are very, very adaptable, but it comes at a
Yeah.
cost. So, cost in many different dimensions. There could be one angle where you look at how you develop and deploy intelligent robots to take over or supplant elements of what's being done by a human today. And there is an alternate approach where you sort of take what could easily be done physically by a robot today, but then recognize it's little pieces of existing manual work that can be done by a robot, and now you have this integration challenge, and then developing AI to help ease those integration challenges. And a lot of those integration challenges occur because humans are the ultimate uncontrollable entity. So being able to adapt or reason explicitly over the uncertainty and what a human will do becomes really important. And a key part of doing that is being able to, for the robot, specify like what are the true constraints that underlie the task that needs to be done and what's acceptable for working with the person. Um, and then if you have a predictive model of what the person will do, that's all the better. Because then you can, you can plan over a time horizon, whether it be less than a second or tens of seconds, and um, the interaction can be a little more fluid. You the like the Baxter is an example of one of these collaborative robots that are really game changing because they're safe enough to be right alongside a person. You don't need a cage, you don't need to remove them physically from the same space as people. And we've used the universal robot in some of our deployments. We really enjoy the Franca Emeka robot. But many of the installations of these robots are still working independently of people in production environments. They're not working interdependently. And because of that, they're limited in the value they can provide or the places they can be easily deployed. And so a key motivation of our work is enabling that interdependence, but rather than forcing the person to like adhere to the fixed, robot
Yeah.
motion or robot
Yeah.
schedule, allowing the robot to accommodate the natural flexibility or uncertainty that a person brings.
Hmm. And now the scenario that we've talked about thus far kind of creates this picture of a human with their kind of partner robot working on some task together. But does it, to what extent do you envision it extending to teams of, one robot embedded within a team of humans, or multiple robot, one human with embedded within a team of robots, or a more diverse mixture of humans and robots kind of working together on some kind of task?
Yeah, the work that I've been describing so far around the techniques for the non-parametric Bayesian techniques for inferring latent state and their dynamics. That is the PhD work of Vaibhav Anholkar, who is currently an assistant professor at Rice University. And actually, even though many of those studies end up being one to one person, one robot, the motivation for a lot of our work is the recognition that you know um, a lot of our work is done in teams, and we do need to know more than just the sort of cognitive state or mental state of one partner in order to succeed. Um, so then that raises really interesting questions about like what is a team cognitive state. And how do you model that, and how can the techniques developed for modeling like one black box agent like a person extend to modeling this sort of like this team concept. The prior work on team performance and team coordination and communication, those settings, maybe other than the pilot co-pilot narrow scenario, those are all team settings involving more than two people. And there is this notion that team cognitive state is something different, and a lot of thinking and study about like what's encompassed in a team cognitive state. And Vaibhav and I have a really exciting collaboration with Harvard Medical School, looking at their operating room and like cardiac surgeries and the very complex dynamics involved in that. And the researchers there, they have this like super futuristic surgical simulation environment that they train the residents in, and grants from NASA to study human teamwork and failures in human teamwork from a human factors perspective. And we're in discussion currently, and Vaibhav Unholker in particular has a really exciting recent working paper out of his new lab in again these synthetic scenarios, but in extending these techniques to model some aspects of team cognitive state, workflow disruptions, sort of missed communication or signals among a team that have adverse outcomes for a team's performance. And again, you have this really interesting question of training time versus online, and like what can be predicted with batch versus online, and with what fidelity, and how does that flow into actually training a new surgeon to identify the team factors that affect performance? Is it done like an after action review, or is there a way to bring these techniques actually online in an operating room and show some aspects of like current coding or rating of the team state that can help, potentially help potentially spur sort of a repair action online that might be useful. Um, yeah, it's a great question, and work that is newer and early underway.
Yeah, it sounds like there are elements of that that are kind of fundamental psychology research,
Yes.
like, what is team cognition separate from the individual cognition, the cognition of the individuals on the team, and what would a representation of that, even start to look like?
Yeah, yeah. The work on that is, so the frameworks that exist for it are not computational frameworks currently, but we've had one of the great joys, and I think from the work in our lab is um, talking with researchers in cognitive psychology and also cognitive science, and sometimes those works really have like the sort of the basis for that sort of that feature identification problem that you raised. We've had success in, for example, taking dialogue acts related to shared understanding, developed in the behavioral psychology and cognitive science literature, and use that to develop an inference system to be able to infer a team's state of understanding of like a common plan that they're discussing. Um, and so there is a lot of opportunity to leverage the decades of research and insight developed in these other fields, and work together to develop computational models that can advance the automated capability of systems to shore up weaknesses that human teams sort of naturally have in performing these challenging tasks.
You've also done some work on in the domain of cross training between humans and robots. When I hear that, I think a little bit of like imitation learning, but I think your approach is in a different direction than that. Can you talk a little bit about that work?
Yes, yeah. So my lab explored this idea of cross training or team training applied to human robot teams. And this goes back to the very start of the lab. And the researcher that did this research was a master student in my lab at the time, Stefanos Nikolaidis, and he's now an assistant professor at USC. And the motivations of that work was, if you looked, then at techniques from the literature and learning from demonstration, it would be like a person showing a task to a robot or walking a robot, through the steps of the task. But if your goal was interdependent action between a person and a robot, like how do you demonstrate that, right? Like it's like you'd be like, okay, robot, you do this. Okay, now I'm gonna do this. Okay, and then what you're gonna do is do that, and then I'm gonna do that. It becomes kind of awkward to think through. And when you look at again the teaming literature, we have many well honed techniques, like tried and true techniques for training humans to work interdependently in very challenging tasks. And it's not always possible, but the gold standard is this thing called cross training. So I do my part of the task, and you do your part of the task, and we try it out together. But then we switch roles. Then, like, I do your part of the task, and you do my part of the task, and we do that for a little while, and then we switch roles again. And it turns out, from a perspective of optimizing human learning for humans learning how to work in teams, this works better than just about anything else. And you can only really do it with small homogeneous teams. Like a nurse really can't take a surgeon's role, but when you have kind of small homogeneous teams, like this is the way to train your team.
I
um,
imagine part of the rationale is that you kind of develop empathy and understanding of the other role, and it helps you, like we talked about before, kind of subtly adapt the way you do
yes,
your thing
yes, yes,
to the
yes.
needs of the partner.
Exactly, exactly. Like when I do your job, I suddenly realize, like, the challenges of you doing your job when and then you come back and you adjust the way you do things for the benefit of the team. Exactly. Um, and so, one of our goals early on was to think about, well, how can you optimize human robot team performance in following this type of learning curve? And so the first try at this was to say, well, what if a human just gives the robot inputs the way a human would experience inputs when working with another person through cross training. So in that paradigm, first the human did their role and the robot did its role, but then the human took the robot's role in a simulation environment and like pretended to be the robot, and then the robot did something that the human would do. The ability to improve the quality of the human's mental model of the robot was substantial. We were able to show that in experimentation, but there was also some evidence that the inputs the person was giving in this modified reinforcement model were of higher quality than you would get through standard approaches to reinforcement learning, which is positive and negative feedback or reward. And that's because if a robot does something and you say like good robot, like there's questions as to what you mean by good robot. Was it good robot for the thing the robot just did, or is it good robot for the thing that you think the robot is about to do next? Whereas when you take the equivalent of those inputs from the person actually doing the robot's job, that's more like a direct demonstration of the person for the robot.
Was this project implemented in simulation, or is there a physical implementation of this?
Yeah, so the cross training was implemented in simulation. So the person and robot kind of played together in this game environment, and the robot, in simulation, showed the movements it would make but they weren't physically working together. It was in a 2D simulation environment, and
Mhm.
then we had the person walk over to the lab to the physical robot and do the task with the physical robot after training under different paradigms. And when the person and robot trained via cross training and simulation, there were both objective and subjective measures benefits to the physical interaction between the person and the robot.
Mhm.
So that leads to an exciting direction where you can imagine a person and robot, or a person teaching a robot and then learning to collaborate with a robot entirely in simulation off the assembly line without money flying by, and then you just walk out onto the assembly line and like you're good to go. You've built your mental model of how to work with this robot, and it's
Yeah,
learned its model of how you'll behave when working with it.
nice. What are some of the things you're most excited about looking forward?
That early work in the lab and cross training, we still have the goal of optimizing a human and robot's ability to co-learn how to work together. That early work in cross training was a part of the reason we pursued it in that particular way was because, like, what does it mean to optimize a human's learning of how to work with a learning robot? Like, I didn't know, but I knew that via certain structured interactions a human should learn better. And so we implemented cross training and we're able to show this really strong benefit. um, Much of our work since has been looking at trying to more directly support and optimize the human's learning via the approach I mentioned earlier about enabling a person to guide a machine learning's model ability to align its learned model with the human mental model. So, how can we learn a machine learning model a latent model that is well aligned with the human mental model directly, not not indirectly via exercising certain forms of interaction? And the question you raised about how you do this at runtime is really exciting and really interesting. On the physical side, I have a group in the lab focused on this, because if you say you're on a automotive line, which we were, and you want to gather your model of a person doing the task so that you can introduce the robot, you have a chicken and an egg problem, because when you collect your data of the person doing the task on their own and then you introduce the robot, suddenly the person does their task entirely differently because the robot is there. It's like out of distribution. So then we're like, okay, so we had these real associates come through, and then we're like, okay, here's what we're gonna do. I'm gonna be the robot. here, look, I'm moving like a robot. You do your task like you would with me as the robot supporting you. And then you try to get your data that way and learn the
Mhm.
model. And then you introduce the actual robot, and then the person does it differently again. And so the ability of a system to be able to follow or even guide that learning process of a person to work with the robot becomes very important, very practically important to
Yeah.
successful deployment of the system. And then we have a line of research also looking at deep models, neural models, and following a similar line of research, like what are the inputs a person can give to shape that latent space so that it better aligns with a human held mental model that's useful for some specific task. So moving from the Bayesian graphical model to deep models, and and enabling that same capability there. But all towards making these systems much more easily shapeable and adaptable to the needs of someone who's not a machine learning expert.
Well, Julie, thanks so much for joining us and sharing a bit about what you're up to. Very
Thank you
cool
so
stuff.
much for having me.